So we'll first introduce the basic formalism, PCFGs, and then we'll talk about a crucial algorithm, which is called the CKY algorithm. And this is, again, actually a dynamic programming algorithm, which will allow us to use PCFGs to parse sentences. So here is a PCFG, and you'll see that it basically looks exactly the same as a context-free grammar, but we now have probabilities assigned to each rule in the grammar. So here I have a set of context-free rules, and we'll again assume that S is the start symbol under the context-free grammar. But now in red I've shown a probability for each rule. So S goes to NP VP, for example, has probability 1. VP goes to VI, has probability 0.4, and so on and so on. These probabilities have one critical property, which is the following. If I take any non-terminal in the grammar, so let's take VP for example, there are a number of possible ways of expanding that non-terminal. So VP can be expanded in 3 different ways here. It can be written as VI, or VTNP, or VPPP. 3 possibilities. And notice that the 3 probabilities associated with these 3 different options sum to 1. So 0.4 plus 0.4 plus 0.2 is equal to 1. And this is the key constraint on the probabilities in a PCFG. If I look at any non-terminal, we must have these probabilities summing to 1. Here's another example. It's NP. Can rewrite in 2 different ways, either as a determiner followed by a noun, or a noun phrase followed by a prepositional phrase. These 2 probabilities sum to 1. So these probabilities have a clear interpretation, which is the following. They are the conditional probability of, conditioned on a particular non-terminal. We have multiple different ways of rewriting that non-terminal. We now have a distribution over those different options, over those different ways of rewriting that particular non-terminal. Okay, so then we can do the following. So let me just illustrate this definition down here, or this text down here. Let's take a particular parse tree under this grammar, very simple one. So notice that every one of the rules I'm using here is in this grammar. So that's a valid parse tree under the underlying context-free grammar. We're now going to assign a probability to this entire parse tree, which is simply a product of probabilities for these different rules. So if I look at the first rule, S goes to NP VP, that has probability 1. And then NP goes to determiner NN, that has probability 0.3. Determiner goes to the, has probability 1.0. And so to calculate the probability of an entire tree, I just multiply together the probabilities for the different rules. So VP goes to VI, has probability 0.4, and VI goes to sleeps, has probability 1. Okay, so that's the final expression for the probability of this particular parse tree. So more abstractly, if a tree has rules, alpha 1 goes to beta 1, alpha 2 goes to beta 2, up to alpha n goes to beta n. This is the left-hand side. This is a non-terminal for each rule. This is the sequence of non-terminals on the right-hand side. Then the probability for the tree is the product of these parameters. So I write Q. So for example, Q of VP goes to VT and P is equal to 0.4 in this grammar. So each rule has a parameter, Q of that rule, which is some probability. The probability for an entire tree is the product of these Q terms, just as I illustrated here. So one useful intuition behind PCFGs is the following. We can now think of top-down stochastic processes under which we can sample parse trees or derivations under a PCFG. So recall that S is our start symbol, so a derivation always starts with S. Now at each point in the derivation, I'm again going to pick the leftmost non-terminal in my current derivation, S in this case, and I'm going to use some rule to expand that symbol. So let's say I pick this rule here, S goes to NP-VP. And we can think of this as a probabilistic process where we choose this rule with the probability under the grammar. So in fact, there's only one way of expanding S as NP-VP, and so with probability 1, we're always going to rewrite this as NP-VP under the grammar I showed you on the previous slide. Next step in the process, we take the leftmost non-terminal again, NP, and you can again think of a stochastic process where we choose the rule expanding NP from the different possibilities using the distribution under the grammar. So in this case, we might choose NP goes to determine NN, so notice that NP is now replaced by these two words, these two symbols, and that has probability 0.3. Now we pick DT, we choose a rule from the grammar. This actually rewrites as though with probability 1, and so on and so on. So this probabilistic top-down process is going to terminate when I end up with a sequence of words. So now at this point I have no non-terminals left. The parse tree underlying this, of course, is S goes to NP-VP. It's going to be something like this. And the probability is going to be the product of these different terms. So you can, in fact, once you have a probabilistic context-free grammar, sample derivations from that context-free grammar in this sort of top-down process. So you can use a probabilistic context-free grammar to generate parse trees. Okay, so some crucial properties of PCFGs. Firstly, as we've said, they assign a probability to every possible parse tree allowed by the underlying context-free grammar. So to calculate the probability of a parse tree, I just look at the rules in that parse tree and multiply together the different probabilities. Most crucially for our purposes, we have the following. So say I have a sentence S. So let's say, for example, it's the dog saw the man with the telescope. So this is our sentence S. This sentence may have several different parse trees under the underlying context-free grammar. So let's say we have a couple of different parse trees, which I'll just sketch here under the CFG. And as we said, this is the ambiguity problem. The problem is that our grammar is generating more than one parse tree. So I'll call this entire set of parse trees T of S. Okay, so T of S is the set of possible parse trees for this input sentence. Now critically, now I have probabilities on these rules in the grammar, I can calculate the probability of each of these parse trees. So I might, for example, calculate the probability of this one as 0.01, and maybe this one is 0.00057. And so now I get this additional information where each parse tree in the grammar, each parse tree for this particular sentence has a different probability, and that gives a ranking on the different parse trees in terms of their probability or likelihood. And so given this ranking, I can, for example, simply output from my model or from my parser the highest probability tree under the model. So I now have a way of choosing between different parse trees. And so the parsing methods we'll look at will first somehow learn the parameters of a PCFG from data, and then given a new sentence, they will search for the parse tree that has the highest probability under the grammar. And if the PCFG does a good job of modeling the probability of different possible parse trees, we'll end up with an accurate parser that more often than not resolves the ambiguities that I just described to you in the previous lecture. So one last definition: if we have the sentence S, then the most likely parse tree for that sentence is, if we look at all trees in that set T of S, remember T of S is the set of possible parse trees for S, we now just choose the highest probability tree under our PCFG.